Here's 2018 question 4. By the looks of this is a Riemann sum table problem. Here we go. We want to estimate h prime of 6. Okay, so remember 6. We don't have the equation, so we can't really get the derivative. So our next best thing is to find the average rate of change. So the 2 points closest to 6 is going to be 5 and 7. Okay, so one version would just be 11 minus 6 over 7 minus 5, or you could flip both of those as long as you correspond, okay? That's enough for equals equal. They do ask us to interpret the meaning of. Okay, so let's take a look at this here. 11 minus 6 is a measurement of meters. 7 minus 5 is a measurement of years. Okay, so now we need a little bit of context. So we know what that answer means in terms of units, but what is it really talking about? They're talking about the height of a tree. Okay, so we know something about the height of the tree. Okay, so the height of the tree. Now, just to give it a little bit more context, I'm going to compute this a little bit. This is going to come out to 5 over 2. Or more importantly, positive, okay? So I know that my derivative is going to be positive, which implies that h will increase. Okay, so I know that the height of the tree is increasing at a rate of 5 over 2 meters per year at t equals 6. Okay, here's part B. Explain why there must be at least one time t such that the derivative comes out to 2. So again, the statement here, is it possible for this to happen? Explain why there must be at least one moment. Right away, that's either going to be IVT or MVT. Okay? Now, since I'm dealing with just h of t here and they're asking me for the derivative, right away I'm inclined to use MVT. Okay? So what I do is, well, first, does MVT come into play? Is the function continuous and differentiable? So they state that right about here. So we know that it works, but that's not enough to say that it'll happen. So what we have to do here is we have to strategically pick 2 points where the average rate of change will also come out to 2. And that'll work right about if you use these 2 points here. And there's really no way of figuring out that shortcut. You kind of have to just stare at it for a while. If I look at 3, 2 and 5, 6, if I found the average rate of change, that's going to be 6 minus 2 over 5 minus 3, which comes out to 4 over 2, which is 2. So graphically, what's happening here is you have this curve. You guys just found the average rate of change is 2. So since the function is continuous and differentiable, it guarantees that there's a tangent line somewhere where the derivative, where the slope of that tangent line will come out to 2. Okay, so there you go. You want to include the average rate of change, and you want to mention about MVT there. All right. Here's part C. They want us to use the trapezoidal sum to approximate the, be very careful here, average height. Okay, so what we're estimating here is, now the first part you don't have to write it. We're trying to estimate the height of the tree from 2 to 10, but to make it an average, it's going to be 1 over 10 minus 2, which is 8. Okay, you don't have to write that first part down. Okay, but you do have to include a 1/8. So here we go. Trapezoidal rule, it's going to be 1/2 times the horizontal distance between the first 2 points. So in between 2 and 3, that's going to be 1 times the sum of the 2 bases, so 1.5 and 2. Okay, I'll do one more. The next one here is going to be 1/2 times the horizontal distance, which is 2, times the sum of the 2 bases here, 2 plus 6, and then you keep going. Okay, I won't do the rest. You keep going, and then you should be done. You can leave it there, equals equal, okay? Here's the last one. Part D. The height of the tree, okay, can be modeled by this function here. Okay, where x is the diameter of the base, okay? When the tree is 50 meters tall, so right away I know that the height of the tree, let's see, g is going to equal 50. When the tree is 50 meters tall, the diameter of the base of the tree is increasing at a rate of. Okay, so let's translate this. The diameter of the base of the tree is increasing at a rate of. So I know that it's a rate, so right away I'm going to write d something over dt. What rate are we talking about here? What's changing? So in this case it's the diameter, but just so that we're not confused, I'll call this capital D. Okay, we know that this comes out to 0.03, but we know it's going to come out positive because the function or the derivative is increasing. Okay, according to this model, what is the rate of change? Let's read some more. What is the rate of change of the height of the tree with respect to time? Okay, so let's talk about this again. It's a rate, so I know it's going to be d something over dt. But what's changing, right? It's the rate of what? The height of the tree. So in this case, the height of the tree is going to be g. We're looking for this, all right? So we pretty much have everything we need here. So here we go. G of x, okay, is going to be 100x over 1 plus x. So here, notice how everything is in terms of x, right? So just keep that in mind. Here we go. We're going to take the differential. So this is going to require the quotient rule. So we start with the bottom times differential of the top, 100 dx, minus the top times differential of the bottom, which is just 1 dx, all over bottom squared. Okay, now everything is with respect to time, so just keep that in mind. Okay, so we want to plug in, what do we want to plug in, right? What does x represent? So x is going to be the diameter, okay? So x right here is the diameter. Now the thing is, they don't tell me anything about the diameter, not explicitly at least, okay? All they tell me is the height of the tree. So you have to do a little bit of digging. Here we go. I know that the height is going to be 50. But what I need is x. And you guys could do this in many ways. You could just solve it by observation or cross multiply and solve for x. But x comes out to about 1. Okay, if you plug in 1, take a look. 100 times 1 is just 1. Down below is going to be 2. 100 over 2 is just 50, okay? However you get that, it's up to you. So when I plug in 1, here we go. That's going to be 1 plus 1 times 100 times dx dt minus 100 times 1 times dx dt all over 1 plus 1 squared. So dx dt, okay? dx dt, remember x was the diameter, okay? So I guess I should go back here. I use capital D as the diameter. So in this case, it's really that. I know that dx dt at that moment is going to be 0.03. Equals equal. It looks really messy, but you got the job done. Okay, that's pretty much it. They don't ask for units. You're all set.